I think today's topic is one of the most practical ones that you will learn in this course. And the reason for that is that the nature of the elements that we have that supply energy. And up till now, we've probably been thinking of those as these sources. They can either be voltage sources or current sources, but those are elements that have the capacity to supply energy into a circuit, although I should say they don't always supply energy into a circuit. But anyway, it turns out that these two different items that we have that we think of as supplying energy into a circuit, the voltage source and the current source, no such thing really exists in either case. Okay? And I'm going to show you some of the reasons why this might be true and how we can deal with it once we learn that maybe there is no such thing as actually a voltage source, or maybe there is no such thing as something that is actually a current source. All right? By way of introduction to this topic, what I'd like to do is show you a few ways that you can actually interface a AA battery. And a AA battery, by the way, is a thing that is we would think of it as a voltage source in a lot of contexts. We think of a battery, a AA battery, or any other kind of battery as being something that can supply a voltage, and that its voltage that it supplies, we think of it as being some relatively constant value, regardless of whatever we hook up to it. Okay, I'm going to show you right now that that may or may not be the way they really behave. Okay, so let me pull this up real quick. This is a multimeter. And I'm going to show you how I can hook this multimeter up to a little AA battery. Okay? So there's my little AA battery. The first setting that I'm going to put on, or that I'm going to set this multimeter to in order to test this battery, is what you might expect. I'm going to put it on DC volts. Okay? And some of you are familiar with this meter. With this meter, anytime you're using any of these settings other than this one over here that says DC 10 amps, we have these leads set like I've got them right here. And all I'm going to do with this first step is to just basically test what this voltage is across this battery with these little leads. Okay? And what do we have? Okay, it says there we've got 1.512 volts. So with my first little multimeter that I've got drawn up here so we don't forget this, here's how I had it set, right? I had the little setting over here on DC volts, okay? I used my little leads and I connected the negative one over here to the negative side of this battery, and I took the positive one and I connected it to the positive side of the battery. Just like this, okay? And then the result, once I measured that, was 1.512, I think I remember seeing it say. Okay? And that's measuring in volts. All right, now a lot of times when I first encounter students wanting to use this meter and they want to measure voltage, a lot of times they get tempted to look over on this side of the meter over here, and it actually says battery load test. If you can see that right there, it says battery load test. And for a AA battery, it nominally puts out 1.5 volts. Okay, so it's very tempting to want to set this over here to 1.5. Okay, 1.5 volts for the battery load test. It doesn't look much different on the screen. It still looks like it's measuring voltage, and it is. Okay, but now when we put these leads across this battery, my guess is we are going to see a voltage that is not quite the same as what I just tested using my DC voltage setting. Okay, so let's see what that does. Okay, first of all, it does actually make the little check light up right there, meaning that it says it's a good battery, but what's the number it gives? Not 1.512, instead now it's at 1.498 volts. Okay, and just to show you that it wasn't a fluke, I can set it back over here and it'll probably be closer to what I tested the first time. Okay, or I can set it back over here and it's always going to test a little bit lower. Okay, I'm going to show you why that is. Okay, so let me do this. I'm going to, with my next little picture right here, I'm going to set this arrow to where it's over here on battery load test. and we got 1.498. Okay, hooked it up the same way, right? We still had the negative to the negative of the battery. We still had the positive to the positive of the battery. But we had the same kind of hookup, and yet the voltage that it reads there is a little bit different. Okay? And before I leave this concept of the multimeter, let me show you one other test that I'm going to give you caution here and say, be very careful about doing the test that I'm about to do. It works on a AA battery, okay? And that's because a AA battery only has so much energy delivery potential. If I was to do the test that I'm about to do on something like an automotive battery, we would probably see smoke, okay? And so I'm going to just give you that warning. Don't do this across a heavy-duty battery, but I am going to do it across this little AA to make a point, okay? I'm going to shift this lead. Here, I'll pull this up real quick. I'm going to shift the red lead here. Instead of it being where I had it in the first place, I'm going to shift it over to that 10 amp setting over there. And I'm going to shift this knob over to where I'm measuring that DC 10 amps, okay? Now, if you had a very conscientious teacher who taught you circuits way back in 120 or something like that, they probably told you to never put a amperage test directly across a voltage source. Did they tell you that? Okay. The reason they told you that is the same reason I just told you. Generally speaking, this might cause some smoke. It just so happens that with this setting on this meter, I am able to measure an amount of current that this battery will supply, and the battery does not have enough energy to make anything break. Okay, so that's why I'm doing this. I just want you to be careful to not do this unless you know what you're doing. Okay, so I'm going to take my leads here and put them across this battery, and what do you think we're going to measure? Okay, amps. And what's my number of amps? Okay, the longer I hold it on here, the more it's going to drop. Okay, do you know why it's dropping? I'm discharging this battery heavily right now. Okay, so it'll just keep on going. What number do you want to pick there? Just 4? Okay, I'll just put 4 on there because it did cross through 4 as we went along. Okay, so when we had this thing set to where the little arrow was over here at 10 amps, and we had the leads set up like this, where this lead went to that side of the battery and this lead went to this side of the battery, what we got was something like 4. Although it was dropping quickly. Okay, now let me explain why we get different values here whenever we do these different tests. Okay? When you are using a multimeter and its job is to tell you DC voltage, right? When we were on this very first setting with DC voltage, inside the meter, the best way for that meter to look to the rest of the circuit you hook it up to is like an open circuit. Okay? Why do you think that might be? Let's say you're doing some tests on a little circuit network and you have some fairly large values of resistor that are in this little resistance network, and you take your meter and you try to test voltage across one of your resistors in the network. What happens if the meter is anything other than a really, really large resistance value? Well, what it'll do is the multimeter itself will start becoming another resistor in the circuit, and it will change the value that you are trying to read. So for that reason, when you are set on DC volts, meters are made in such a way as they try to have extremely high effective resistance to current flowing through them when you're on this DC volt setting. So essentially, if you kind of think of what goes on inside this meter, it's close enough to say it kind of comes up in here and we have an open circuit internally inside of this meter. Okay? Now, it turns out that when you measure a battery to try to figure out whether or not it's any good, even batteries that are bad, that are not really able to produce much energy anymore, even batteries that are bad often will look like they're putting out a certain amount of voltage if they're not required to push any current, right? So if you have your meter set up like this, it's intentionally trying not to let the battery push current through the meter, right? But what your battery has to do, if your battery is going to be any good, is to push current while still maintaining a voltage. So knowing all of that, how do you think they change the meter so that they try to, make it more useful for a battery load voltage test? Why, like when we shift this knob over to the battery load test over here, inside the meter, what does it look like now? Something like this, where it intentionally puts a path for current to go through once you hook it up to a battery. And what that had the effect of doing for this battery is it had the effect of actually dropping the amount of voltage that we were able to read once the battery had to push current through that little resistor. Okay, so that's kind of interesting. Now, before I move on to kind of explaining how we can model one of these batteries and, in a way that helps us to understand how it really works, let's think about the current test that we did, right? When you're measuring current using a multimeter, what is the best strategy as far as what the meter should look like to the rest of the circuit? If you're the maker of the meter and you're trying to make it so that your meter is good at measuring current without messing up your measurements, what do you need the meter to look like to the rest of the circuit? A short circuit, right? You want to make it so that it passes current through it without restriction. Okay? So inside the meter, when you have it set to measure this current like this, it's like it's a short circuit. Okay? And that's on purpose so that the meter is capable of making good readings for current. All right? So now let's look at all of these relationships here. And I'm going to introduce an idea that I think will help you resolve how all of these different values can be on this, on this multimeter. If instead of thinking about a battery as being just a voltage source, what if we think of a battery as being a collection of an ideal voltage source? So think of inside of this battery, not that this is what's really inside of there, but think of, in terms of the theory of it, that it's got an ideal voltage source that connects inside of here, but then in series with that ideal voltage source, we have some little value of resistance. And I'm going to go ahead and give that a name. I'm going to call it R sub S. Okay? Down here, this little voltage source I set up, I'm going to call that V sub S. The sub S that I'm using there it stands for source. So that's the voltage that I have inside the source, and then the resistance that I have inside the source. If that meter really works like I kind of represented to you that it would, then how much current flows through R sub S? Any thoughts? Is there a path for current to flow around a circuit in, case number 1? No. So really what I've done there is I've set up a voltage like this that goes through a little resistance, that's R sub S, but then it immediately doesn't have a path to go through. So this is Vs, this is Rs. Now here's my question. What voltage should I see at the terminals of that little, network that I've made right there? What voltage would I have right here? Okay, I'll call it Vm for the voltage for the meter. Okay, no current is flowing, so what voltage is dropped on Rs? 0 volts are dropped on Rs. So if I then do a sum of voltages around this loop, it's not technically a loop because it's not closed, but you can still sum voltages around it, right? What should I have for Vm? It's equal to Vs. So the number that I got up here, the 1.512, that is roughly what that hypothetical ideal voltage source is inside of that battery. Does that make sense? So this is going to be equal to Vs, which means that for that battery I was just testing, it's probably got about a 1.512 volt. Think of it like a hypothetical ideal source inside of there before we consider anything that has to do with internal resistance. Okay? What about my next case when I'm doing the battery load test? What would this circuit look like? Okay. Here I've got my RS again. And now what do I have it going through over here? Okay. This is the resistance that is set up inside of that multimeter. So maybe I'll call that R sub M. That's the resistance of the multimeter in that mode. Okay. Now what would I say I probably have for my actual ideal voltage source that's inside the battery? Still 1.512 volts probably, or something like along those lines. Okay, but now I'm driving that voltage through the combination of the internal resistance in the battery and the resistance of the meter. And what we're seeing when the meter reads, we are seeing the voltage that drops right here across these two terminals, right? So when we see the 1.498 volts, we are seeing that voltage at the input of the meter. We're not seeing how much voltage gets dropped on the internal resistance for the source. Okay, is that interesting? What happens now in the last case? .512 probably, something like this, volts, going through this internal resistance, and then how does it connect? Short circuit, meaning that we probably have about 0 volts here. Okay. What does that mean? If there's 0 volts there, where is the voltage dropping? Okay, across that internal resistance of the battery. As a matter of fact, you weren't able to feel it, but as I did that test, the battery was heating up. What do you think that was about? Okay, you're driving current through a resistance, that battery starts heating up. So anyway, that so that is still RS, but we're saying that it has a voltage drop across that RS that is 1.512 volts or so. Okay, so here's my question. If that's 1.512 volts dropping across that resistor, and we measured a current of 4 amps, that's a current that goes around this way, right? 4 amps. About what value is that of RS? Okay. RS, you know, any resistance is going to be a voltage divided by a current, right? So if I take 1.512 volts divided by 4 amps, what that tells me is that, you know, at least for that test, it looks like the internal resistance of that battery was roughly 0.378 ohms. Okay? So we'll say RS is roughly 0.378 ohms. Okay, and that value, I mean, it can shift a little bit because technically there's not like a little resistor inside of there, right? What you're seeing is actually just the nature of the battery, and we're modeling it as if it's a resistor. Okay, but that number doesn't change a whole bunch, so it's, you know, somewhat valid to come over here and say that RS is still going to be equal to 0.378 ohms in this test. So what does that mean RM might be? Okay, is there a way to figure that out? Okay, well, can we use voltage division? Right, what I'm saying here is that we have 1.512 volts, right? Well, let's say it this way, 1.498 volts should be equal to 1.512 volts multiplied by what? Rm over Rm plus 0.378 volts. So what's Rm? Being that resistance internally in the multimeter. Okay, well, you can do this a number of different ways. Here's probably the easiest way I can think of, is I can say 1.498 is equal to 1.512 times X over X plus 0.378. And I entered that improperly, so I'll do it one more time. All right, X over X plus 0.378. Okay, and what I should have done the first time was hit Shift Solve and then equals. Okay. So maybe something like 40.4 ohms or so. Okay, and just to kind of reiterate, the VS I found in the first place was 1.512 volts, which I used in my subsequent steps. All right. So my point with all of this is to kind of get you comfortable with the idea that a battery is this different kind of voltage source, and the name we're going to give it is a practical voltage source, meaning we can actually produce a voltage source that behaves approximately like an ideal voltage source in series with some kind of resistance. We are not capable of making a voltage source that produces the same voltage no matter what kind of current we demand out of it. So this is our way of sort of dealing with that. Okay, in terms of the analysis of it. All right, now let me do this in a little bit more kind of circuits theory terms here. Let's look at some characteristics of ideal sources versus practical sources. I'm going to do this first with a couple of possibilities. So the first one that I'm going to look at here is a voltage source, and I'm going to ask you, what happens if I take this ideal voltage source and I hook up a wire across it? Okay. What will happen? Okay. Actually, our theory has nothing to say to us about this because we've just done something impossible. Why? There's no resistance in that little wire I just hooked up. The job of the voltage source is to hold a voltage, let me call this Vs right here. The job of the voltage source is to make sure that we always hold Vs across those two terminals. What's the job of the wire? The job of the wire is to make sure there is no voltage across those two terminals. Which one wins? Okay. Answer is, it's a dumb question. Okay. Because we can't make a voltage source like that, right? Nor do we have wire that truly is resistance free. So it's kind of a silly question, although it does help us think about what happens if we, kind of push things that direction. So anyway, let me kind of put a few things up here. If this is, I'm going to call this thing over here like a load resistance, RL. Okay? And what I've just done there is I've said RL is approaching 0. What happens now to the definition of resistance here? V over I is equal to R. Okay? What happens now, if you think about RL going to 0, what happens now that can make, or V is just some constant value, right? So what's the only way that I can make this R go to 0? I has to approach infinity. So that's practically what starts to happen if you try to do this with something that is your best attempt at a ideal source, and you hook it up with your best attempt at a resistance-free wire. Current will start to trend toward infinite. And that's when you start to find funny things happening. The magic smoke comes out a lot of times if that goes on. Okay? So that's kind of interesting. Let's look at, we saw this a little bit with the battery. Just because it's impossible in terms of the theory doesn't mean you can't try to hook up just a wire across a battery. What happens, though, is that we have, in our actual sources that we have, practical ones, right, we have this little internal resistance RS, and we have a VS right here. So now if we hook up just a wire across here, that wire's job, again, is to hold their 0 volts across these two terminals. Is that an impossibility? Okay. It's not. We actually saw something a little bit like that when we did our current test with the battery. Now the amount of current that the ideal source inside the battery is pushing is only limited by its own internal resistance. Okay. And so what we find with this is that what we'll have is that so a lot of times we're going to talk about these in terms of this variable IL, meaning the current through the load. 0 volts here is actually VL, that's the voltage across the load. Okay. And so what we have there is now that the current across the load here is going to be what? Okay, we did this already when we did our example with the battery, but it's just going to be VS over RS. Okay, so this is no longer an impossibility for us to think about that as a source with a wire just going directly across it. Okay, before I leave the point of these voltage, the practical source versus the ideal source, let's look at another way of thinking about this, and that is, what if I let RL, in this case I showed it just being a wire, but let's say that instead of thinking of it as just a wire, I think of it as possibly having some kind of a, non-zero resistance value. Okay, and I'll call that RL. Okay, so if I call that RL, what happens with this VL versus IL relationship if I was to plot that? And then I'm plotting it as RL changes value. Okay, so my first example was with this being just a wire going straight through, right? That would be RL going to 0. And what did we find we had for I? Okay, it went infinite. What would happen with this circuit if I let RL go to 0? Excuse me, the other way, go to infinite. What voltage do we see across here if RL is infinite? Just the voltage source. So I'm going to go ahead and put here, let's say I have VS. The way this ideal voltage source behaves is that it's going to hold this value regardless of how much current flows. Okay? What happens with a practical source? If I do kind of a similar thing here. VL versus IL. Okay? Again, what if I let RL go infinite? Meaning infinite resistance across that little hookup. What happens with the value that I will have on this plot? Just like I had before, it's going to start at VS, right? There's still going to be VS across the terminals of the load if I allow the RL to go infinite. But now what happens as I let RL trend to 0? It will start to taper off the amount of voltage that I see at the load until I go to 0, which is the limiting case I had right here. This was for, that was for when RL goes to 0, IL goes to VS over RS. So this becomes a straight line that comes down like this, and when I hit down here, the current that I have for RL going to 0, that's what happens right there. The current that I'm going to have is VS over RS. Okay, and the current that I had up here was 0, and this is what happens when RL goes infinite. This kind of makes sense? All right, let's do another one now, but for a current source. And I should say this before I really dig into the current source. We actually have devices that are closer to being ideal voltage sources than we do that are close to being ideal current sources. I couldn't do a similar test like what I just did with a battery just now and say, here's my thing that approximates a current source. Now let me do all these tests on it. We don't have something like that. But we do have batteries that are close to voltage sources. Okay, so that's often a question that comes up, so I'll just go ahead and address it head on there. Okay, first of all, for this little ideal current source that I have right here, my first question is the circuit that I have shown right there even possible? I say circuit, I maybe should say network, right? That circuit is not possible. Why not? There's no loop, and yet, which by itself isn't a problem, but it's a problem because why? That current, it says, I'm going to drive this current, I'll call it IS here. It says I'm going to drive that current no matter what. And yet, the fact that I made no connection right there says there is no place for current to go. Okay? So, my next question is, that is what will happen, if we try to do this, first, maybe I'll say it this way, it can't happen. So what will it try to do then, this current source? We can test what it will try to do based on thinking, what happens if I put a really big resistance right here? Okay, let's say RL that I put right here it starts approaching infinity. So now it's not infinity yet, it's just approaching infinity. What happens now to the voltage across this load? Okay, again, we can kind of think of it as V equals IR, right? Now we have R going to infinity with I being a constant. What's going to happen? VL will also approach infinity. Okay, so what will happen if we actually have a current source, something that's trying to be a current source, and it will literally produce as much voltage as it needs to until it can drive a certain amount of current. Practically what will happen if we have these two leads sticking out in the air, eventually there will be enough voltage that you will cause there to be an arc across the two leads. It'll turn the air into something that will conduct when air is not usually something that will conduct. Okay? So this is kind of the direction it will go. It's basically impossible for you to have a perfectly ideal current source, but this is kind of the direction it will go. Before I move on to what a practical current source might look like, what would the little graph look like here if we think of voltage versus current? Okay, depending on what value you have for your RL, let's say you have RL equal to 0. What are you going to have on your V versus I plot? how much voltage, if I make RL 0, how much voltage will I have as VL? 0, because that's the wire's job, right, is to hold there to be 0 volts right there. So I'm going to start at a value here of IS. Now what happens as I start increasing RL? It'll just go straight up. It will keep producing IS regardless of how much RL I put in the circuit. Okay? And it'll go up to as much voltage as you need to make sure that that IL is flowing. Or IS, equals IL, I really should say for this, but okay. So that's kind of the direction that that ideal source would want to go. How does it really behave once you have more of a practical current source? Okay. The way we model a practical current source is we take an ideal current source and we imagine having a resistance in parallel with it that we're going to call RS. And then out of this comes what you would hook up additional things to, like a load resistor. So this is IS in parallel with RS, and then if we have some kind of a load that we want to hook up to this circuit, we would put that over here as RL. Okay. By the way, load, when I use the word load, what we're talking about is a device typically that needs energy, right? So the circuit is doing something and it's, it would like to deliver energy, power to that load resistance, right? So this is how a practical current source is built. And let's think about now, what would this VI relationship look like for this practical current source? Again, this is for the load itself, IL being the current that flows down through here, just like it was in the first case, and VL being the voltage across it. All right, so this is VL versus IL. Okay, now let's take our limiting cases. What happens if RL goes to infinity? Will any current flow on IL? If RL is infinite, right, that will keep any current from flowing around this little leg over here, IL. So I will have 0 IL if I, have an infinite RL. And what voltage will I have for VL? Where will all the current go? Through RS. And so what voltage will be across RS? Okay, again, we're taking the case where RL goes infinite. So we're having all of our current now going through RS, and the voltage is going to be IS times RS. Right? So I'm going to put that little dot right here and say this value is IS RS. Now what happens if I take my RL and let it go to 0 instead? I just did the case first with RL going infinite. Now what happens if I let RL go to 0? Okay. If I let it go to 0, it will not let there be any voltage, because that's the job of a wire, is to not let there be any voltage, right? Lets as much current flow as needs to make sure there's no voltage. Okay. And what will the so there's 0 voltage. What will that current value be over there? Okay. If there's 0 resistance to current flowing on the load leg of this circuit, then how much of the current IS will flow on that leg? All of it, right? So the value that you're going to have down here is IS, okay? And that's going to happen when RL approaches 0. this up here is what happens when RL approaches infinite. Okay? All right. Does that kind of make sense? Like what the effect is of adding these resistors in for our practical sources versus our ideal sources? Any questions before we move to the next thing I want to do? All right. I wanted to do this next, is talk about a real-world example. And this is, actually easier to see in the wintertime than it is in the summertime. So with a little bit of cold weather out there, this is something some of you might have seen. If you have a car that has headlights that turn on automatically once you turn the key of your car to the on position. Okay, some of you probably have that, some of you don't, but let's say you've got a car that as soon as you turn the key to the on position, your headlights come on. Okay, and they stay on. And then you get ready to start your car, so you actually switch it over to the start position on the key. What happens to the brightness of your headlights? Okay, they look dimmer. What's going on? Okay, let me actually kind of explain this to you with some numbers that are somewhat realistic. Okay, for your battery, inside of the battery, it is going to be a practical voltage source. That's what the battery is in your car. So inside of this thing, you have a little ideal voltage source, right? And it's connected up here to this battery post. And then it goes through a little resistance value of some kind before going up into that post. Again, that is not like there's a resistor inside of there. What it is that it really has to do with the chemical process that has to go inside of that battery. That process, if you demand that it drive at a certain rate or higher, it will start to decrease how much voltage it puts out. So it's not like there's really a resistance in there, but it behaves as if there's one. And so the values that you can typically expect for a battery like this usually is something around the lines of 12.2 volts for the voltage of the ideal source that's inside of that battery, and then maybe something along the lines of about 2 hundredths of an ohm for the resistance that's inside of there. Okay. How much current do headlights typically draw? It varies a little bit, but let's just use a general value here. Headlights probably draw somewhere around 10 amps of current. Okay, how much does your starter draw? Okay, again, it varies somewhat depending on what kind of engine you've got and a lot of other factors. Let's say somewhere in the neighborhood of about 150 amps. Okay. So let's think of what these voltages are going to look like in this circuit, right? Because your headlights essentially are just in parallel with your starter motor. And there's a starter switch there that's not closed to begin with. So what kind of voltage do your headlights see once you just have the headlights on, but not the starter yet? Okay. Well, what you're going to have is basically 12.2 volts minus what? Okay, I'm going to label this voltage, headlights only. Okay, how much voltage is going to drop on this little internal resistance in the battery with the 10 amps that are being drawn with the headlights? Easy, it's an easy calculation, right? 10 amps times 0.02 ohms. Okay, so what'll that be? 12.2 minus 10 times 0.02. 12 volts. Right? Everybody's happy because that's what we kind of think of the system in your car is probably usually around that amount of nominal voltage anyway. You're still happy. What about now the voltage that you see with the headlights and the starter? Okay, 12.2 volts minus what? Let's say this was 150 amps once that switch closes, right? Okay, that would be 160 amps, let's say in rough terms, times 0.00 or 0.02 ohms. Okay, about how much voltage are we going to see across the headlights now and across the starter? Okay, 9 volts. That's why your headlights dim. Isn't that cool? It's because the battery in your car is not truly a voltage source. It is just a pretty good practical voltage source, right? That means it can produce a lot of current and still stay somewhat close to the amount of voltage it's supposed to be. All right. By the way, there can be other resistances in line too. Some of you might have dirty battery cables. What is that going to do? Like right here where you've got your cables connected, instead of there being zero resistance at that connection point, what can happen? You can have a little bit more resistance right there. And what's that going to do? It'll make your car harder to start a lot of times. Or maybe it won't start at all if you've got too much resistance in those battery cables. Okay? All right. Anyway, I like that example because it's a place where you've actually experienced maybe a real voltage source as opposed to one that is ideal. All right. Now, this is a really cool thing here, is that we can actually set up an equivalence between practical voltage sources and practical current sources if we just make one little conversion as we move between these two. I'm going to show you how that works right now. Okay. In the left case, I have a practical voltage source connected to a load resistance RL. And in the right case, I have a practical current source connected to a load resistance RL. Okay? And what we're going to do here is we're going to try to see what the VL and IL will be in each one of these cases. Okay? So what is VL? And I'll define VL as being the voltage across the load. Okay? What is that going to be for my practical voltage source? Okay, what is this circuit essentially? We used them all the way back in the freshman year. This is a voltage divider, right? And so we have a nice clean equation for voltage division. What do? Vs times RL over what? Rs plus RL. This is just voltage division. Okay? So far, so good. And what is IL going to be? Okay. Yeah, you can just use Ohm's law now if you want. IL is just VL, right, divided by what? Okay, it's just Vs times RL over Rs plus RL. Okay. And then what did we say? All of this divided by RL. Now, what does that do? What happens with RL? That just divides out, right? So IL is just going to be equal to Vs times 1 over Rs plus RL. The other way that I could have gotten there is to just figure out what the equivalent resistance is across Rs and RL. It's just the sum because they're just in series. And Ohm's law would say that you have just Vs over the equivalent resistance would be Is, or IL, either way. IL is just the current around this loop. Okay, so basically, we don't really need that intermediate result. I'm just going to let this be these two results right here. Now, what about the current source? I'm going to start actually with IL. Okay, IL is this current that flows through the load. What's IL going to be? IS times what? RS over RS plus RL. This is current division, right? And what is VL going to be? VL being the voltage across that load resistor. Okay? Yeah, all it is just all of this stuff, IS times RS over RS plus RL times what? RL. Okay? Now, what happens if I take that VL equation and it's the same equation, but I rearrange it just a little bit and say VL is just equal to IS RS times RL over RS plus RL. What I want to show you there is this ISRS. If I think of that as being VS, then essentially VS could substitute in there and these two equations would look the same. Right? So this kind of gives us a little bit of a, maybe it gives us pause to think a little bit and say, what if VS was equal to ISRS? Does that still work for the currents? Like if I was to replace anywhere I see VS, I replace it with ISRS. Does it work when I get down to my current equations? Right? Where do I have VS? Right here? Would it be valid to say here IL is equal to ISRS times 1 over RS RL? How you can tell if these are equivalent circuits is we should have exactly the same current and exactly the same voltage equations. What is it that allows that equivalence to happen? Okay, there's only one equation that makes that happen. It basically says VS is equal to IS RS. And this allows us to convert a voltage source, a practical voltage source, to a practical current source, or vice versa. Right? You can actually take a practical voltage source and convert it to a practical current source, or take a practical current source and convert it to a practical voltage source. And this actually winds up being an incredibly powerful analysis tool. Okay? You want to see how that works? Here's a big old circuit. I've got 3 different sources in there, 2 voltage sources and 1 current source. And the instructions say find the current flowing in RL and the power that it absorbs. Okay? And I'm going to write up here, and so that we don't forget it, I'm going to write VS is equal to IS RS. And what we need to look for is, do we have any practical voltage sources or current sources, or some combination thereof? Do you see any practical voltage sources or any practical current sources? Or multiples? Okay, what does a practical voltage source look like? It's an ideal voltage source in series with a resistance. Okay, so anytime we see an ideal voltage source in series with a resistance, you can say, that's a practical voltage source, right? What happens if you see a current source in parallel with a resistance? That would be a practical current source. And you can convert anytime you see a practical current source to a practical voltage source, or vice versa. Anytime you see a practical voltage source, you can convert it to a practical current source. Okay? So why don't we start and just do one and see if it changes our outlook on this circuit. I'm going to identify this one right over here and say it looks like we have this resistance right here is actually in parallel with this current source. Right? See how they share a pair of nodes right there? So how do I convert that current source into a voltage source? Practical one. Vs is equal to ISRS. What's Is? 4 amps, right? For this one that I just identified. What's Rs? 7 ohms. So when I do this, I should come up with a Vs that is 4 amps times 7 ohms. What would that be? 28 volts. Okay. When you do this, the resistance value doesn't change. You keep the same resistance value. The Rs that I had over there, you're going to keep that Rs value of 7 ohms. Okay? And what we're doing here is we're thinking of how we're connecting from this blue node down here up to the yellow node. What happens once we connect it up into the yellow node? What does it connect to next? That 1 ohm resistor. Then from there, where does it go? Okay, way over here to this node over here. Tell you what, I'll color the rest of my nodes so that we're comfortable with everything. Okay, so there's all my nodes color. Actually, I still have one bit more to do down here. Okay, so this thing comes down and connects in with that green node up there. And so I'll tell you what, I'll just do that real quick and I'll leave everything else alone. Here I've got my 6 volt source going through my 3 ohm resistor, connecting up into this node right here where I've got my 9 ohm there, goes down into a, make sure that polarizes right. This goes down into a 27 volt source right there. And then this goes over to my 4 ohm resistor. Okay. Well, now what can you do? This is an equivalent circuit because all I did was I replaced my practical current source over there on the left with a practical voltage source. But now what can we do? Can you combine these two resistances? And if so, how do you do that? They're just in series, right? So that's 8 ohms now. All right? Now, what it looks to me is like we've got 3 practical voltage sources that are all in parallel with one another, feeding a 4 ohm resistance. How do you feel about converting all of those practical voltage sources into practical current sources and keeping them all in parallel? Does that sound like a plan? How do I do that? Okay. Well, a practical current source looks like this, where we've got a current source, an ideal one, that's in parallel with a resistor. I just said this one was an 8 ohm resistor, the one on the far left. I can't put 28 amps on this current source over here. What do I need to put for my current? Okay, Vs equal Is Rs, right? Rs is 8 ohms. And what is Vs? 28 volts. So my Is that I will have right here is going to be what? 28 divided by 8. Okay, 3.5. Now this is going to be in parallel with another practical current source. Okay, there I've got my 6 volt source with a 3 ohm resistor. What I'm going to have there, I keep the 3 ohm resistor and I add an ideal current source here in the same direction. I didn't mention that on this last one. The direction of the arrow has to match the polarity of the voltage source that we are replacing. Okay, so it needs to point the same direction up there. And what value should I put for that current source? Vs equal Is Rs. Rs is 3 ohms. Vs is 6 volts. This would be 2 amps. Right? 6 volts over 3 ohms would be 2 amps. Now what? This goes in parallel with my 27 volt source in series with my 9 ohm resistor. Now the polarity of this source is reversed, so I'm going to show the direction of this arrow the same direction as the polarity of that last source. And I'm going to put that in parallel with that 9 ohm resistor. And then all of this is going to be in parallel with the 4 ohm resistor way over there. What value should I put in for this current source? 3 amps. Okay. Now, because I have all of this stuff that's all in parallel, how do I combine current sources, ideal current sources, when they are in parallel? They just add, right? Yeah, but you have to make sure you use the signs right according to what the arrows do. So we basically have 3.5 amps up plus 2 amps up. That'd be 5.5 up. And then what? 3 down. So that leaves me with 2.5 total up. Okay. And then how do I combine all of my resistors except for the one that I want to know about, right? I'm supposed to find the current flowing in RL, so I don't want to include RL in this last step. But I want to combine all my other resistances that I have, the 8 ohm, the 3 ohm, and the 9 ohm. What do I do for that? This is going to be equal to 1 over 8 ohms plus 1 over 3 ohms plus 1 over 9 ohms. Because I have all those resistors that are all in parallel with one another. And then this is all going to be connected up to my 4 ohm resistor over here. So what is this going to be? Okay. 1 over 8 plus 1 over 3 plus 1 over 9. That gives me 1.756 ohms. So how much current flows on my 4 ohm resistor? IL is going to be 2.5 amps, times what? I'm going to do current division here again. 1.756 ohms over 1.756 ohms plus 4 ohms. So IL is going to be whatever that turns out to be. Let's see. I'm going to store this into A, and then I'll do 2.5 times A over A plus 4. That'll be 0.7627 amps. Okay. But it asked for another thing too. What else did it ask for? It says the power that it absorbs. How do I get that? Okay. Most of you are familiar with the equations for power, one of which is current squared times resistance, right? So I can take 0.7627 amps squared times 4 ohms. And y'all don't need to see me punch that in. What I have set up for that, or what I have calculated for that, is 2.327 watts. So what I've just shown you now is using practical source transformation as a circuit analysis tool. And the only equation you really need to know is that to convert from voltage to current or from current to voltage, the only factor you really need to know is what is that practical source resistance, right? You keep the practical source resistance when you go from one to another, but you just have to change what the voltage or current is going to be on the source, on the ideal source that's a part of it. Okay? We good? Okay, let me take this a little bit further. Think what happens now as we imagine again changing the value of RL. Okay? And then we already did this once, but what would this curve look like for VL versus IL? Okay? Just remind ourselves one more time for this practical voltage source. If you have 0 for RL, right, it means that VL is going to be 0. Right? And I is just going to be equal to Vs over Rs. Okay? And what happens if you have RL going infinite? It means you have 0 current, right? You'll be up here on this end of the curve, and you are going to have a voltage that is just going to be Vs. Okay? Now here's an interesting thing. Power is, what's the formula for power, the most general one for electricity? P equal IV. And what we're doing here is we're doing this all for this curve right here. This is all for the same circuit component. This is like that load resistor RL. So I could put little subscripts on all that and say PL is equal to VL. And what this means is if we get right up close to, let's say, 0 resistance, right, just letting current flow all through this resistor right here, what is a way to graphically show the power that is being delivered to the load resistor? Okay, if we get RL going close to 0, that's going to be down here at this end. And the power that's going to be delivered is going to be this, you could represent it graphically with like a little rectangle here, right? But because you're getting very close to 0 amount of voltage, how much power gets delivered? As it approaches 0, you're going to approach 0 power delivered, right? What happens if you let RL approach infinity? What happens then? You're going to get close to this end of the curve up here, and what is the area of that little rectangle going to trend toward? 0. Okay? So if you have too much load resistance, you're going to deliver 0 power. If you have too little load resistance, you're going to deliver 0 power. Okay? Does that mean we always deliver 0 power? Okay, let's take a third possibility. What if you're somewhere here in the middle? Your power you're delivering is graphically represented with the area of that little rectangle for some other value of RL, right? Not 0, not infinite, some other value of RL that's not 0 or infinite. Okay? How do we figure out two things? One, how much power could we deliver maximum? Because, right, we go from 0 back down to 0, but somewhere in the middle it's not 0. So that kind of gives us the idea that there must be a maximum somewhere. So how much power can a practical voltage source, in this case, deliver maximum? Okay. And then what value would we need to have for RL in order for it to deliver that power? Those are kind of our interesting questions that we're going to try to set up here. Okay? Let's do it kind of with a similar start to what we did when we first looked at how we could transform between practical current sources. Let's come up with values for VL and IL. So VL, we said earlier, was VS times RL over RS plus RL. Okay? And what was IL? Okay, it's going to be equal to just VS over RS plus RL. We already did that when we were looking at transformations between voltage and current sources, practical voltage and current sources. Okay, so now based on these, what is an expression I can come up with for PL being the power that is absorbed in the load resistor? Okay, what do? Just multiply them, right? And if we multiply these together, what do we end up with? Okay, VS squared RL over what? RS plus RL squared. And what I'm trying to figure out is, where is this going to maximize? How do we do that? How about this? How about we take a derivative? And we're going to take the derivative with respect to RL, because that's the variable that we're thinking about varying to try to come up with what the maximum power delivery is. Okay. What is this going to be? Okay. What we're operating on there looks to me as though it is a quotient. So what do we need to do? Okay. Well, how does the quotient rule work? Maybe I'll do that up here real quick just to remind us. Okay. Okay, what you do, I won't do it. I'll say you take the two parts, right? Let's call them gx and hx, g of x and h of x. You take the derivative of one and multiply it by what? The other one not derivative. Then you take the other one, the one you took the derivative of first, you take it and multiply it by the derivative of the second one, and then take the whole thing and divide it by the denominator squared. So here's what that looks like in this case. Okay. What's the derivative of the numerator of PL, this PL equation here? Is VS controlled by RL? It's just, with respect to RL, VS is just a constant, right? So we can just leave that alone, but when we take the derivative with respect to RL, okay, what does that do? We're left with just VS squared, right? So that's one of our terms. Then what? Okay, I took the derivative of the numerator, multiply it by what? The denominator all by itself, RS plus RL. Okay, so then what do I do after that? Subtract, okay, the derivative of the denominator. What's the derivative of the denominator? That's kind of more messy, isn't it? What's the denominator? RS squared plus 2RS RL plus RL squared. What's the derivative of the denominator with respect to RL? 2RS plus 2RL. And what is that going to multiply by? The numerator, but not the derivative of the numerator, right? So that's going to be VS squared RL. Okay, and in the denominator, I have RS plus RL, now to the fourth power, because I'm taking the square of the denominator. And I'm going to set all this equal to 0. Tell you what, I want to save a little bit of time here. So I'm going to take a page from one of my previous professors, Dr. Lee, and say after many dot. Okay. What we end up with this is an expression that says RS squared minus RL squared has to be equal to 0. What does this say? RL has to be equal to RS. This is the condition for maximizing power delivery to the load. The load value, the value of the load resistance should be equal to the value of the source resistance if you want to maximize how much power you deliver to the load. Okay? Now, this also wastes a bunch of power, right? So I need to make sure you understand that too, right? This delivers equal amount of power to the load resistance as it does to the source resistance. Okay? And that's not necessarily a good thing, because now you are delivering as much power as you wanted to go to the load. This is the exact amount of power that's also being delivered to the source resistance, and what's that going to do to the source? Right? It'll probably make it heat up. And maybe it's up for that, or maybe it's not. So, you know, anyway, but hypothetically, in theory, if you match these two resistance values of the source and the load, then that's going to maximize how much power you can deliver. Okay? Let's do one more example where we use that. Okay? For this example right here, it says find the value of RL that would maximize its power absorption in this circuit. Assuming it has that value, how much power will it dissipate? Okay? An interesting thing to kind of throw in here is that in some of your problems, it will use the phrase, tell me what the maximum power you can deliver to a well-chosen load resistance. So what does that mean you have to do first? You have to probably figure out what that resistance is. Here I stated a little bit more explicitly what I wanted you to do, but I just wanted you to hear that phrase. find the maximum power that can be delivered to a well-chosen load resistor. Okay, that says essentially the same thing as what I wrote out longhand up here. First, find the resistance value that you need to make that happen, and then find how much power gets delivered in that case. Okay, so where should we start with this problem? Let's try using our technique we just learned with source transformation. Okay, I'm going to start over on the left side of this circuit. Let me transform my 20 volt with my 12 ohm into an equivalent current source, practical current source. Okay, so here we're going to have a current source in parallel with a resistance of 12 ohms. Okay, and that's going to be in parallel with the other things that were in this circuit, right? The 8 ohms, the RL, the 5 ohms, the 6 ohms now in parallel over here with the 2 amps. Okay, now to complete out this equivalent circuit, what do I put in for my current source over on the left? Okay, what I'd want to do is essentially take that voltage 20 and divide it by 12. Okay, 1.6667 amps. Okay, now what does that allow me to do here? Can I combine these two resistors right here? If so, what do I do? Okay, one way to do it is you can take 12 ohms times 8 ohms over 12 ohms plus 8 ohms. When you do that, I got that comes out to be 4.8 ohms. So you can replace those two parallel resistors with a 4.8 ohm equivalent resistance. Then what can you do? How about you convert back, right? So because I have this current source now in parallel with a this resistor, right, of 4.8 ohms, that means I can take that resistance times the current. Okay, and that tells me that this is going to be an 8 volt source over here. Now in series with a 4.8 ohm resistance. Okay, now this is going to go in series with the RL, which is in series with the 5 ohm. This is going to be in parallel. Now I'll tell you what, I'm going to skip a step here. Can I do a source conversion for the 2 amp and the 6 ohm? Okay, what would that look like? 6 ohms here, and then what? A voltage source down here that is going to be 6 ohms times 2 amps. And what will that be? 12 volt. Okay. Now what do I combine? Okay. I've got a bunch of things now. Technically, the 5 ohm, the 6 ohm, and the 4.8 ohm are all in series with one another, as are these two voltage sources. So that means I can convert all of this to 20 volts, because that's 12 volts plus 8 volts, going through what? Okay. Yeah, 11 here plus 4.8, 15.8 ohms. And then this is going to go through our load resistance. What do I need to put in for my RL to maximize power delivery to RL? Okay. You plug in the same value you had for the source resistance, which was 15.8, which, by the way, 15.8 ohms is the answer to the first part of the question. RL for maximum power is going to be 15.8 ohms. Okay? So you plug in that 15.8 ohms, and when you do, how much voltage do you have dropping on each of the two resistors? Okay? It's simple because they're equal to each other. Each of them drops 10 volts. So, how much power gets delivered to RL? $10 volts squared, this is V squared over R. 10 volts squared over 15.8 ohms. Okay, this gives me 6.329 watts. So in that example, what we did was we had to pick a resistance value to maximize our power, and then that power winds up being 6.329 watts. Yes, sir? Okay, his question is, when you combine the 8 volt and the 12 volt, does it matter that the polarities are different? Okay, so my question is actually this: are the polarities different? Okay, it's drawn in a different way than you might be used to seeing it, right? But what you do is you imagine tracing along this way, right? And you encounter the negative sign of each of these elements first as you trace along around that series circuit, right? So that tells you that the net effect is going to be additive, not subtractive, because you encounter the first sign you encounter as you trace along that direction is the same for both of those sources. It's, those are in series with each other and they are additive. Okay? What else? What other questions can I answer? All right. Thank you for your attention.